Three key design decisions were taken when making alterations to the initial glider. First, we decided to add the elevator with a single cut, and in doing this, we reduced the number of weak points on the tail as well as the design complexity. This also allowed us to attach just one servo, thus reducing the need for any linkages to other moving parts. Having a single part also ensures that the deflection angle is constant across the entire elevator and there is no control input lag. The second key design decision was the placement of the servo. We decided to place it as close to the aerodynamic centre as possible, which we assumed to be at approximately a quarter chord length behind the leading edge. This was in order to minimise the additional lateral moment its presence would create. The final key design consideration was where the ballast would be placed. The main ballast added was at the nose to move the centre of gravity forward, thus increasing the lateral stability. Attempts were made to add the ballast in a way that is symmetrical about the longitudinal axis. The first series of experiments were to determine the best CG position in terms of stability by adding masses to the nose of the glider. Here is the table for our first experiment. 4 CG locations were tested and the stability was noted. We kept the elevator deflection as 0 at all times. At the leading edge, we found the glider to finally be stable. We then started experimenting with elevator deflection to try and achieve trimmed flight. We tested 4 deflection angles as summarised in the table. Found to be at 47% of the mean aerodynamic chord, and our CG is at the leading edge, therefore giving a static margin of 47% of the mean aerodynamic chord. A positive static margin means our aircraft is stable, and we opted for such a nose-heavy configuration to create more stability and less elevator authority, as it was quite difficult to obtain accurate measurements of elevator deflection.